from Poisson's equation to power amplifiers using ASM-HEMT model is all about this new industry standard ASM-HEMT model. This has been my research for over 10 years now, and this workshop presentation will introduce this particular model to new users and also give latest advancements in this model to users which have been exploring or adopting this model. Several companies are adopting this model for their technology. These are commercial foundries and also research labs. And this talk will introduce this model to new as well as experienced users. So let's get on with it. This is the outline of my talk. I will talk about first different types of models. This is actually to give a background of the benefits and advantages of physics-based compact models, which ASM-HEMT is. I will compare different styles of models on some figure of merits for compact models. And then I will get on, into ASM-HEMT compact model. I will introduce the model, present a user level view of this model, and then into more details about different components of ASM-HEMT model, how it is built, and what are the major connectivity among different components of this model. And then from user point of view, the nonlinear RF extraction of this model. So this is the title of the talk. I mean, it goes from Poisson's equation in creating the model, and then doing a nonlinear RF extraction and using the model for simulation of power amplifiers. Now, with the extraction flow presented, I will present sample model results from several commercial GaN-HEMTs. These are big companies, small companies, research labs, different people adopting this model and the kind of results which we have achieved using this model. And then there is an interesting aspect of using the physical foundations of this model to closely connect device technology to the circuit design. So I will present two examples of such kind of co-optimization or novel capability which this model, because of its physical foundations, allow. And then I will conclude my talk. So device modeling is like a link or a connection from device technology to the circuits and products. To design circuits and products, design and optimize to get the best out of a particular device technology, you need to do circuit simulations. Circuit simulations allow optimization, but such simulations are based on the device models, the models of devices which are used in that particular circuit. And device model, the accuracy, the capability, the limits of circuit simulations are all dictated by device models. You need circuit simulations to be fast. You need the models to allow them to scale many aspects of the technology. You want the models to be robust, converging. And all of those aspects depend directly on device models. Now, if you think about device models, they can be broadly, very broadly divided into these three categories I have here. These are three-dimensional TCAD models, measurement-based models, and physics-based compact models. 3D or two-dimensional TCADs capture very fine details of a technology. You can see this is a representation of device, and then the device is broken down or divided into a very large number of mesh points. The device physical equations are solved in each and every mesh point, and then the simulation results of this self-consistent solution, IV or charge or whatever you want to simulate is given out. Measurement based, on the other hand, are something you measure, you make the device, measure the device, and that itself can be used as a way to simulate the behavior of the device. You may also have some simple empirical formulations, just like the one shown here, which is a polynomial fit, to simulate the device. Physics-based capture key features of the technology, such as field plates or the T-shaped structure shown here. The formulations themselves are actually derived from fundamentals of device physics. Examples of physics-based models are ASM-HEMT and BSIM PSP compact models, which are BSIM and PSP are for silicon technologies. So these are the three broad categories. And if you think about the figure of merits from a user point of view, the model should have these four figure of merits. They should be fast, so speed is a figure of merit. They should be scalable with respect to the geometry and different aspects of the technology. They should be accurate globally with respect to different biases and different temperatures, and they should be robust in circuit simulations. Now, the different categories of models fare differently on these figure of merits. For example, TCAD models are highly scalable because they capture all these fine details, a large number of mesh points of the technology. They are globally accurate for the same reason, but their speed is poor because, again, there's large number of mesh points and the simulations have to be self-consistently performed at all of these mesh points. They're also not as robust because the large number of mesh points and satisfying the convergence criteria becomes harder and harder as you have larger number of mesh points. Measurement-based models, on the other hand, they can be very fast. They can be very fast because they are very simple mathematical formulations. However, their scalability is limited by the data taken. Their global accuracy is limited by the data taken. And their robustness is also poor because the mathematical formulations can be too simplistic, which may lead to non-convergence problems where the measurements are not taken. And usually this is the case that for circuit convergence, the simulator is going to take models in areas where you have not really measured the device into. Physics-based compact models are striking right balance among these different requirements. So they can be scalable, not as scalable as TCAD, but significantly more scalable as compared to measurement-based models because they are derived from fundamental physical formulations. They are globally accurate. They have a reasonable speed, not as high as measurement-based, but reasonably high speed because the formulations are analytical. Then, if they are created right, they can have good circuit convergence because fundamental formulations such as the charge conservation is built into these models. So ASM-HEMT is a physics-based model, and it is a new industry standard model selected by a standardization body named Compact Model Coalition, or CMC. CMC runs a very rigorous multi-step process which ran over almost 5.5 years. And now this model is available in several major simulators and modeling environments. So as a user, how does this model look like? So as a user, if you think about this model as a black box, you need to supply bias and temperature, bias that is VGS, VDS conditions, model parameter values, and then you can simulate different aspects of the device. It can be current, capacitance, nonlinear, harmonic balance, or whatever. Now, the parameters of the model themselves can be divided broadly into these three categories you see on the screen. First is device geometry, because the model is built from physical foundations. It needs the information about the technology or the geometry of the device. This is length, width, number of fingers, axis lengths, and things like that. Then there are parameters which are directly linked to physical effects, such as mobility, this is carrier transport, saturation velocity, pinch-off voltage, and parameters like that. Then there are third category of small number of smoothing or fitting parameters, because to get to analytical equations, you need some approximations which lead to smoothing parameters. So these three categories, once you supply this information to the model, you can simulate different aspects of behavior. Now, because of the physical foundations and geometry being an input parameter, physical effects being an input parameter, the model is significantly more scalable as compared to measurement or empirical approaches. Now, getting more into the components of this model, the components of ASM-HEMT model can be, it can be thought of as three main components. First one is the core model. Second are models for physical effects in the device. And then the third one are additional capability for advanced simulations. The core model is actually, the charge calculation or surface potential calculation in the quantum well of the GaN-HEMT device. The core model also includes the carrier transport. So this is the mobility and the saturation velocity aspect of the device. Now the core model actually assumes the device to be ideal device. That means no self-heating, no access region resistance. So the core model to model an actual real device has to be augmented with something called as real device effects. This includes access region, non-linear access region resistance models, self-heating, channel length modulation, and many different effects. These two are, modeled, the formulations are such that they are self-consistent with each other. And then the third is to advanced simulation capability, which includes thermal noise, flicker noise, and variability. So all of these components are coded, are implemented into the formulations in a single self-consistent ASM-HEMT model code. So these are the main components of this model, and they are self-consistent among each other. Going a little more into detail, it can be the model arrangement can be also thought of. There is a core formulation, and then around the core there are many real device effects as listed here. So real device effects, like I already mentioned, nonlinear access region resistance. There are field plates are used in GaN-HEMT device, so there is a configurable field plate. So different device technologies can have different arrangements of field plates, and model allows you to do that. I will talk more about that. And then many other real device effects. So in this presentation or workshop talk, I cannot go into the details of each and every real device effect. I will cover a few. And then the idea of modeling each real device effects with specific physical formulation is what is main idea, central idea of the ASM-HEMT model, that each and every physical effects is modeled by proper formulations, self-consistent with the core model. So let's look at the core model first, and then we will look at few real device effects, how they are modeled into ASM-HEMT model. So in terms of the core model, as mentioned previously, the core model has to really do with the charge in the quantum well. The charge in the quantum well here, which is also represented by the energy band diagram here. Now, the main challenge to calculate the charge or the surface potential in the quantum well is that the physics equations are transcendental in nature. That means there is no analytical solution available. In this paper, what we were able to do is that we were able to identify that as the Fermi level changes with the applied gate voltage, there are specific regions within that change of Fermi level with Vg. And in each region, one can actually derive analytical formulation by using certain approximations. So this becomes a regional model, but then we were able to also combine this regional model into a single unified formulation for the surface potential or the Fermi level, which is the second figure here. You can see that the unified proposed model has a really good accuracy as compared to the numerical solution. Now, note that numerical solution is actually not good for compact models because we want the speed, as mentioned before, and we were able to derive that analytical unified solution for the surface potential. So this is one of the core formulation. Now, using the surface potential, the 2D EG surface potential, then one can apply carrier transport. So this is the drift diffusion carrier transport which is applied, and you can derive this this type of core model formulation. So you see the psi ds, psi m are surface potentials at different points in the device. This picture here is just that with these formulations we were able to achieve good model accuracy. There are more results to show a similar thing, but these were the initial results with the developed formulations. So this surface potential, and then the core current model, and then next is the core charge or capacitance model. These consist of the core formulations of ASM-HEMT model. Now the capacitance behavior is modeled with charge equations. Modeling the capacitances with charge-based formulations takes care of an important physical phenomena or physical law, which is law of charge conservation. Law of charge conservation is important because if the model does not follow it, it will lead to non-convergence issues. This can be easily shown and has been studied in several research papers. In ASM-HEMT, by design, we use terminal charge calculations which conserve the charges. So it follows inbuilt by design. It follows the law of charge conservation. Now the charges of each of the three terminals of the device are derived using these formulations. Again, these formulations are actually integrated and there are analytical solutions in the model. Now the good thing is that with just one analytical solution, so for example, one analytical equation of QG, you can model CGS, because that CGS is a derivative of QG with respect to VS. As you see here, CGS, I is G and J is S, so that becomes CGS. So this dQG over dVS and CGD. Now CGS and CGD themselves are both functions of VGS and VDS, and this single formulation of QG will model all of this behavior. So you see that CGS dependence on VGS and VDS, as well as CGD dependence on VGS and VDS, is captured with single analytical formulation. This picture just shows that, this is showing for CGD. So CGD, you can see, is a function of VDS and a function of VGS, and that is captured by the developed charge formulations. So these formulations become the core of the ASM-HEMT model, and then on top of these cores, many of the real device effects are built or created, formulated in the model using self-consistent formulations. So one of the real device effect is to account for the field plates in the model. Now the field plates are accounted in a configurable way in the model. So by configurable, I mean that this is a picture of one particular device. In this particular device, there is region 1, region 2, region 3. Different technologies may have different configurations. You may have more field plates, you may have less field plates. So ASM-HEMT model actually allows you to configure the model such that you can have the field plates arrangements you have in your device. Set the model in the way your device is. So users can set different regions of the device to be gate connected field plates. So for example, R1 and R2 are gate connected field plate regions, or source connected field plate. And there are 4 configurable field plates supported in the model each side. So towards the drain, there are 4 field plates possible. Towards the source, there are 4 field plates possible. So there are total 8 field plates which can be configured for in the model, either to be gate or source connected field plates. Now the field plates are actually quite important, and this slide just shows their importance. So this is showing input capacitance versus gate voltage. If you usually look at the device behavior without the field plate, you will get a behavior which is here. This line here, which is very small fringe capacitance, and when the device turns on, you see a rise in the capacitance. This is the main transistor or this particular region of the device turning on. Now, field plates typically have lower cutoff voltages compared to main transistor. So as a result, in a real device with a field plate, you are going to see low capacitance, even for a very low or a negative VGS bias. But then you are going to see this bump. This bump is because of the field plate turning on. So field plate turns on, and then after a while, you keep increasing VGS, your main transistor will turn on. So you see another bump in the CV behavior. So this is captured with configurable field plate in ASM-HEMT model. Next is the modeling of thermal effects. Thermal effects are actually can be divided into two categories. One is the modeling of the effect because of the change in the ambient temperature. Change in ambient temperature is modeled with the physical parameter variation. So for example, if the device is at 25 versus the device being at 125, the mobility will be different. The threshold voltage or the pinch off voltage will be different. And these are modeled in ASM-HEMT formulations. So this is how the model captures the change in device behavior with ambient temperature. There is another effect, another thermal effect, which is self-heating in the device. Self-heating is because of the power dissipation, the local temperature of the device can be much higher than the ambient temperature. And this is actually modeled with this type of self-consistent formulations, self-consistent implementation in the ASM-HEMT model. So ASM-HEMT is a function of temperature because its physical parameters are functions of temperature, like mobility is a function of temperature, pinch of voltage is a function of temperature. And the model itself, the model formulations can give you how much is the power dissipated in the device. Because once you apply the bias voltages, you have the current flowing, and power dissipation is VDS times IDS. That power dissipated is fed to a thermal network. This is a thermal network which captures the transient response of the heating. So there is a time which you need. There's a thermal time constant, and the thermal time constant is captured by the thermal network. Then this thermal network returns the rise in the temperature, and this loop is self-consistently solved in the ASM-HEMT model. So this is how the thermal effects are captured in this model, self-consistently by capturing the change in physical parameters with ambient temperature and the accounting of self-heating with the thermal network. So in summary, I only talked about two real device effects, but there are many. And this includes channel length modulation and drain-induced barrier lowering. But for the limited time, I will limit to only two. The main idea is that real device effects are always self-consistently modeled within the ASM-HEMT formulations of surface potential-based core formulations. For more details, here are the links. So this is the link which lists all the publications, which will describe how different things are modeled in this model. The real device effects, which we did not cover in this workshop, and then you can also look at the manual, which is also given in this link. This is freely accessible, so you can download it for free without registration or anything. Next is something which is more for users, that how do you use this model? How do you extract this model? So these are the main steps in developing a nonlinear RF model with ASM-HEMT. First is you set the device geometry parameters. So you need to know the information about your technology, and you set its geometry parameters as is, length, width, number of fingers, field pad configurations, and few other aspects. Once you set this, next step is to actually extract the drain current model. Now the drain current model is created in a way that different regions of the IV plane, like below subthreshold or below cutoff, above cutoff, linear region, saturation region, have different sets of parameters. So you can follow an extraction strategy for IV extraction. This is given, this is detailed in technical manual. You start with below V off and then you go on to above V off, linear region, saturation region. Once you do the IV model, then you can move on to modeling of S parameters, multi-bias S parameters. So here again, similar to IV, there are different regions of CV behavior, and then parameters of the ASM-HEMT model which capture the CV behavior in different regions. So these two, IV and CV, these two are primarily parameter optimization steps. This is where the actual optimization needs to happen, because first step is just directly setting the model parameters. And the last step is, once you have modeled multi-biases parameters, then you do the model validation or fine-tuning for large signal behavior. I will show some of the sample results which have been achieved following this strategy of nonlinear RF extraction. So let me start with some of the results. First result you see is the IV model extraction. What you see from here is drain current, accurate drain current model, but what you also see is that several orders of derivatives. You see GM here, you see GM dash here. GM dash is the first order derivative, and then you also see GM double dash. That's the second order derivative of the GM, or the third order derivative of the current. So several higher order derivatives are accurately captured for one particular VD, another VD, and third VD. So this is the way the formulations have been carefully built to have accurate, not just the current, but also the derivative. Once you have the drain current, you move on to the multi-bias S parameter. But let me just show you another important aspect of this model. This is the behavior of ASM-HEMT IV model in the third quadrant operation. This is the negative VDS. This is also crucial for RF switch simulations. So once you model the forward IV, the negative VDS of the third quadrant operation is physical, and it's automatically properly captured by the model. So this is also a crucial property for a good compact model. Okay, so once you have the IV, then you build, this is your intrinsic ASM model, and around it you build a parasitic network to capture gate manifold, source vias, and any other parasitic elements related to the wiring or the metal pieces in the actual layout of the device. The extraction flow for these parasitic elements can follow pretty much the well-known either hot FET, cold FET, or the strategy which is based on resonances. We have applied both and achieved good results with both of them for the full nonlinear RF model. So this is what is the general structure, that you have the intrinsic device, and then around it you build the parasitic network to model the full RF behavior of the device. And here are some of the results for a commercial GaN device. This is S11 and S22 from 0.5 to 50 gigahertz. And this is for many different bias conditions. I think for one VD, these are 10 different VG conditions. For another VD, these are 10 more VD conditions. This is one model capturing all these bias regions and frequency points for S11 and S22. Then these are S12 and S21. These are magnitudes. You can see good model accuracy here. And then these are the phases of S12 and S12 for 2 different VG and 4 different VD conditions for a commercial GaN device. So those are the small signal, and these are the large signal results again for commercial GaN device, and actually 2 GaN devices here. One is 20 volt and another 25 volt GaN device. So setting up large signal simulation is pretty much standard. You have the intrinsic model, you have the parasitic network, and just bias tees to set up the biases, and you have the RF power in, RF power out to simulate the large signal model behavior, or P in, P out. So this is P out versus P in. You see a good model accuracy for this technology 1 at 3.5 gigahertz. This is 20 volt technology. And you see good model behavior also for technology 2. which is 25 volt technology. The green lines here were trying to study a specific effect and how that effect is important to model the large signal behavior. In this case, this was actually the VDQ, the quiescent-ring voltage dependence of IV. So these are some of the results. There are some more results. Now this is for 50 volt, higher voltage, 50 volt technology. These are load pull at class B bias and 3.6 gigahertz. So you can see pretty good model accuracy in terms of the output power contours to get to the optimal point, and also good accuracy in terms of P out versus P in for a tuned efficiency load for the top graph and for the tuned power load for the bottom graph. Then, because of the physical foundations of the model, you know, a lot of interest in exploring this model to connect the device technology more closer to the circuit behavior, you know, behavior such as AMPM nonlinearity. So what we did in this particular study, which is published in recently, is that first you model the AMPM behavior with ASM-HEMT, which you see captured quite well. The blue line is the model, and then red dots are the measurements. So you see AMPM behavior is reasonably well captured with the model. You know, as you increase the output power, the nonlinearity increases. Now the source of the nonlinearity itself has been studied in this paper, and we found out that, you know, because of the presence of the source field plate and the way the threshold voltage or the cutoff voltage of the source field region is, it actually affects the output capacitance nonlinearity of the device. The output capacitance nonlinearity, because of this field plate region, we found that if you remove the source field plate, the AMPM behavior can be different. And this is, you know, this type of connection between the device technology, the device features, and actual nonlinear circuit behavior of the device is very tightly modeled and tightly coupled in the using the ASM-HEMT. So this is a new feature of the model, a new capability enabled by the model, which is also gaining a lot of traction in terms of usage to optimize GaN technology further. Another example is this multi-channel RF switch. So in this particular work, we are modeling this device which has vertically stacked multiple channels. This is actually an RF switch device, and using ASM-HEMT based formulations, we were able to simulate and model very accurately the behavior of the device. You can see S21 and S11 for different bias conditions from off state to on state, and what is especially beneficial for this physics-based formulation is that you can now scale and study the effect of number of channels, study the effect of changing this device features into the RF performance of the switch. So this is another work which is recently published using ASM-HEMT. So in summary, ASM-HEMT is new standard physics-based model. We talked about different components of the model. We saw the core and the real device effects, and we briefly went over the extraction flow of this model. I showed different accurate IV, CV, large signal behavior which have been modeled for commercial devices, research lab devices, and I explored or presented some of the new capability which is enabling design technology co-optimization, where the model can be used to study what are the features of the device technology which are how they affect the circuit performance of the device, such as the field plate example or the multi-channel GaN device example. So ASM-HEMT is, you know, being rapidly adopted by different companies and organizations And these set of slides also give links for you to download the technical manual and different publications on this model. And you have my emails, so if you have any questions or any feedback, any suggestions for furthering this model, please feel free to email. And if you have any questions on this workshop, just let me know. Thank you.